Now that we've seen Diffie-Hellman as a concrete example, let's talk more generally about what public key cryptography means. The general idea is that key comes in pairs. There's a private key that I'll draw in a cloud here because it's enshrouded to the rest of the world, and a public key that goes with it. I'll draw a yellow sunshine behind the public keys because it's out in the open for everyone to see. Another standard convention that I'm following in the slides is a lowercase letter used to label private keys and a capital letter used to label public keys. In general, the private key is what's needed to decrypt a message, and the public key is what's needed to encrypt a message. So Alice will somehow send her public key to Bob. Bob will have that, and now Bob will be able to encrypt messages that only Alice can decrypt because only Alice has the private key. Similarly, Bob will send his public key over to Alice so that Alice will be able to encrypt messages that only Bob can decrypt. It's okay for Alice and Bob to send these public keys over the network, again, because they're public. So in our pictures, only things with sunshines around them should be sent over the wire. In Diffie-Hellman, the private keys correspond to these random numbers that Alice and Bob pick and don't tell anyone else. And the public keys that they send back and forth correspond to the mixtures of that private key with some public information, the P and the G that is specified by a particular standard, say. In the case of Diffie-Hellman, the way that the private key is used is that Alice combines the public information from Bob with her private key to arrive at a shared secret. And now Alice and Bob are going to use the shared secret to communicate back and forth. So it's not exactly that every time Bob sends a message to Alice, she uses the private key. Instead, she uses the shared secret. And it's not exactly that Bob encrypts that message with Alex's public key, but that he derives a shared secret to use for encryption from Alice's public key. But now we'll move to RSA, which matches a little more closely this general picture of public key cryptography. When Alice wants to send a message to Bob, she will quite literally use Bob's public key to encrypt a plain text and get to a ciphertext that she sends to Bob. So this ciphertext doesn't mix in anything about Alice, it's based purely on Bob's public key that he has somehow shipped to Alice. Bob, meanwhile, receives that ciphertext and uses his private key directly to arrive back at the plain text. Flipping things around, when Bob wants to send a message to Alice, again, he uses Alice's public key to encrypt the plain text, to get a ciphertext, and only Alice will be able to take that ciphertext with her private key to get back to the plain text. There's going to be an extra thing that we can do with these kinds of keys, which is that Alice can use her private key to sign something and send that out to other people. Other people will be able to decrypt that ciphertext using Alice's public key. So in this case, Alice is not trying to get confidentiality, not trying to send a message to Bob that only Bob can read. Anyone can read this ciphertext because it turns out that her public key also works to decrypt things that are encrypted with the private key. But what it does mean is that if Bob knows, for some reason, that this is really Alice's public key, then only Alice could have encrypted this ciphertext in a way that produces a valid plain text. And how did Bob get Alice's public key? Well, it is public, so maybe Alice has had it posted on her webpage forever, and so Bob has good reason to believe that that really is Alice, who has controlled her webpage for a long time. Or maybe there is some shared directory that Alice and Bob are both consulting. We're going to come back to this and talk about some specific mechanisms on a different day. So RSA is going to get us to not only confidentiality of messages, but also authentication of messages.